Hi, good afternoon, everyone. My name is Dr. Pu Suan Hui. I'm the lead for the Mechanical Engineering program, and I'm also the lead for the Aeronautics and Astronautics program. So today for this webinar, we're going to talk to you about specializations in engineering. If you are interested in becoming an engineer, but you're not quite sure about which particular branch of engineering to go into, this is the webinar for you. So I'll start off by talking a little bit about mechanical engineering and also about aerospace engineering before handing the time over to my colleague, Dr. Low, who will be speaking more about the electronics and electrical engineering specialization. Okay, now when you think about mechanical engineering, what do you have in mind? Okay, so perhaps an image like this, when you think about facilities management and you have an engineer, perhaps working in the oil and gas industry, and he's really looking after the asset of the whole petrochemical complex. So he needs to ensure that the pumps are working well. He needs to make sure that there is no extensive corrosion leading to leakage in the pipes. So maybe this is an image of traditional mechanical engineering, and it is still very critical, very important in this day and age. But what else do mechanical engineers do? Okay, so if you look at this image over here, what we have over here is a wind farm. So mechanical engineering is perhaps one of the most versatile branches of engineering. So starting off with a training in mechanical engineering, you could go off and work in the sustainable energy industry. In this example over here, you have a wind farm. What you are doing is you are taking the power from wind and converting it into electrical power so that we can use it in our daily lives. For a mechanical engineer to be able to design a wind turbine that harvests wind energy, you need to have the fundamentals in mechanics. You also need to have the fundamentals in fluid mechanics as well. So all of that you will get from a mechanical engineering education. So if you look at this structure over here, this image does not do it any justice at all because it looks small from the screens that we are looking at. But actually, if you look at this structure over here, the diameter of this wind turbine is more than 100 meters. Okay, so imagine yourself doing a 100-meter dash. How long does it take for you to cover 100 meters? That is the size of this structure over here. So there is a lot of high-tech engineering that is required to ensure that you select the right materials, to ensure that the shape of the wind turbine is not only good for harvesting wind power, but it is also strong enough to withstand a storm. Okay, so all of that is important, and you cannot just start off with a blank sheet of paper with no engineering training and hope to be able to design a structure like this. All of this is mounted on stable platforms that are scattered out in the sea. So you need to make sure that they are built in a structurally sound way as well. Okay, so mechanical engineers could be involved in sustainable energy now, and going forward into the future, it is going to be even more important. What else do mechanical engineers do? So if you look at this image over here, you see a scene within a surgery theater, and you might think that this person over here, his doctor, perhaps he's assisted by a couple of nurses. So it doesn't look like an engineering workspace, isn't it? But actually, if you look beyond the medical professionals, so actually what you have over here are the robots that enable the nurses and the doctors to perform high precision surgery. Okay, so what this enables the doctors and the nurses to do is something that they cannot do by hand, okay, because of the precision that is required. Mechanical engineers, how do they get involved in this space over here? So if you specialize in biomedical engineering, so starting from mechanical engineering training, you can apply it to medical robotics, and then you can get involved in designing a robotic system that is used in surgery. So again, this is perhaps an area that people don't normally associate with a mechanical engineer. But if you are trained as a mechanical engineer and you have the inclination and the interest, you can actually go into medical robotics. What else? So other than robots that are applied for surgery, you can also have general purpose robots as well. Okay, so if you're interested in the mechanical engineering space, you also have interests in sensors and electronics. You combine those two together, what do you have? You have a mechanical engineer who goes into mechatronics. Okay, and another word for mechatronics is basically robotics. Okay, so over here, two examples of robots that you see in this image over here. So the one on the right is a biped robot, so it's standing on 2 legs. And over here you have a quadruped robot, it's standing on 4 legs. Okay, so depending on the application, where are you going to apply these robots? Okay, so they are designed to be general purpose. Is it going to require additional stability? And hence you might want to go for the 4 leg option, the quadruped option, or do you want it to appear more human-like, and therefore you go for the option on the right. Okay, so as a mechanical engineer, if you are going to apply your knowledge to design robots, okay, you need to be trained in advanced design. Okay, so one example of these robots being used very recently. Okay, so here, this is a park in Singapore, and because of COVID-19, the government in Singapore used this robot over here, the same robot that you see on the previous slide, to check on safe distancing, to make sure that people are not crowding in open spaces. So this robot is now equipped with cameras. It is equipped with all sorts of surveillance devices so that the government can make sure that people are interacting in a safe way. Okay, so this is one example of how this general purpose robot is being applied. Now, coming to Southampton. So at the University of Southampton, our students actually get to design robots that look a lot like the commercial robots that you see in the previous slide. So this is an actual student project. It is done by master's level students. So this is equivalent to year 4 of the Master of Engineering program. So in this project, the students designed this quadruped robot, and for the specification, they are actually planning for this robot to be used in an extraterrestrial context. So for example, if you were to send it to Mars, it needs to be able to withstand harsh environments. It needs to be lightweight. It needs to be equipped with sensors and telemetry functions, and to be able to wirelessly transmit this data back to Earth as well. So this is a project that our students actually worked on, and it is still ongoing. Some of the testing was actually disrupted because of the pandemic, but you can see that even our mechanical engineering students are actively involved in state-of-the-art engineering design. Okay, what else is going to be important in the mechanical engineering space? Okay, so increasingly, lots of major automotive companies are investing huge amounts of money to ensure that their vehicles are going to be smarter and smarter. Eventually, you're going to have vehicles that can be operated without the human driver. In terms of the technical aspects, a lot of the challenges have been overcome. So you see these vehicles being tested on the streets even right now. But you always still have a human driver because of the legality aspects. Those are things that still need to be ironed out before we can fully deploy autonomous vehicles in the real world out there. So technical aspects, a lot of it has been ironed out. Perhaps in terms of the legislation for particular countries, particular cities, that is still being worked on. But no doubt, going into the future, we're going to see cars and even trucks that are operated autonomously. So you might have a whole fleet of lorries pulling your containers going from the port to where the distribution center is. So all of this is being worked on by engineers at the moment. Okay, so if you start with mechanical engineering as your fundamental training, and then you specialize in automotive engineering, and then you go on to specialize in autonomous vehicles, this is a potential career pathway for you. Now, we have seen examples of a few systems that I've talked about. So I talked about a wind turbine to harvest wind power. I've talked about robotic systems. I've talked about medical robots. I've also talked about autonomous vehicles, right? Now, how do you get all of these systems designed and built? So you start with the design process, isn't it? Okay, so going back into the 70s, this is a scene that is very common in engineering. And in fact, this image is taken from a major automotive company, General Motors in the United States. At that period, if you were to design a car, you might have a large room full of designers, engineers, actually working together, leaning across a huge table, sketching out their designs by hand. Okay, so when you start off a mechanical engineering program, we actually let you learn how to sketch a drawing or design by hand, but we move on very quickly into a more modern and advanced method of doing designing. And we make use of computers to help us, so it's known as computer-aided design. But what is special about computer-aided design is that instead of having a large room full of tens or even hundreds of designers, you can now reduce all of that effort to a single designer. So a single mechanical engineer or designer, with the help of a computer, a good computer, and the right software, you can actually perform the work of many engineers. Okay, and you get trained up how to do that if you go through a good engineering program. Okay, so if you look at this image over here, what is this part that we are looking at? So this is actually a high performance motorcycle. So it's a racing motorbike, and this is the brake system. So if you have a very powerful motorbike, you need to make sure that the brake systems are working well, because if you're going at high speed, you need to be able to control the movement of the motorbike, right? Okay, so what is the designer interested in? The designer needs to make sure that the brakes are efficient, is able to get the motorbike racing at high speed down to a slower speed, to a safe level, perhaps. Okay, so you have the brake pads over here highlighted in red. You have the brake disc over here, which is rubbing against the brake pad. And you want to make sure that you dissipate the energy to slow down the motorbike. And you have the frame, okay, and the frame is depicted in various colors over here, and there's a reason for that, because the colors represent something about the structure. But I just want to draw your focus and attention to the shape of this structure in the middle of this whole brake system. Okay, so what is interesting is that as a designer, a single mechanical engineering designer, with the help of a computer, you can actually generate hundreds to thousands of design options within a single day. Okay, and that is something that you cannot do, okay, without the help of computers. Okay, so if you were to join University of Southampton, you're interested in design, this is something that you will be trained to do. Okay, so what are some specifications that are important in the brake system? Okay, you want to make sure that as you are slowing down the motorbike, you are not creating lots of unpleasant noise, for example, squealing noises. Okay, so that's the reason why you see certain holes that are cut out of this brake disc over here. What about this structure in the middle? Okay, you want it to be lightweight, but you want it to be strong. So that is what you can use the computer software to help you with, right? Okay, so you're done with the design, but before you can actually use it, you have to manufacture it, right? Okay, so mechanical engineers, we have a whole suite of manufacturing processes to help us with And in this slide over here, you can see some more traditional manufacturing techniques. For example, casting, starting off with molten material, and then you put it into a mold, and then you allow it to cool and form. We have more general metal forming, which includes forging, rolling, drawing, extrusion, etc. And then you have traditional subtractive machining as well. So you start off with a workpiece. It could be a block of metal, and then you use a mill or a drill, and you cut that block of material into shape, and you arrive at your part. Once you have all your parts manufactured, you can join them together using mechanical fixtures like bolts, nuts, your welds. You can also use high-performance adhesives, and that allows you to put the whole frame and the structure together. It's a little bit like building a toy model, if you have ever been involved in that. Yeah. So this is all traditional manufacturing. It is still important. Now, going forward, additive manufacturing, 3D printing is going to be highly crucial. And in your high school, perhaps you have had the chance to play around with 3D printers, benchtop ones, where you get to print polymers, plastic material, and you basically heat up a filament of plastic, and then you extrude it, and the 3D printer basically puts it down layer by layer, and you end up with your part. Now, it turns out that you can actually do the same thing, not with plastic, but with metals as well. And in this image over here, you see a line of 3D printers that's been set up by General Electric Aviation. So it's one of the major aerospace engine manufacturers. Okay, and they have put together this 3D printing line where they use a laser to fuse together metal powder to end up with a final aerospace component. So 3D printing is not in the hobbyist domain only. It is actually put to real-world manufacturing use, and you can actually use it for aerospace components as well. Okay, so I've put the links down here. There are the videos that you can watch. So I don't have the time to share the video with you, but you can actually go to the links and you can explore an example of how a high-performance 3D printer works. So as a mechanical engineer today, you are required not only to be well-versed with traditional manufacturing processes, you need to be kept up to date with future manufacturing processes as well. And 3D printing is one of the most important ones. Okay, so I've started off with mechanical engineering, so I'm just going to shift over slightly to aeronautical engineering. Aeronautical engineering shares a lot of commonalities with mechanical engineering, which is why in the first year, a lot of the subjects are common. And then thereafter, the two subjects, they diverge. And for aeronautical engineers, basically you are focused on designing aircraft. For aerospace engineers, if you are going to the astronautics component, you are then looking at designing, for example, rocket systems. You're designing satellites as well. Traditional aeronautical engineering, you might have an image that looks like this, a technician or an engineer doing some kind of a scheduled maintenance on an aero engine. But what else do aeronautical and astronautical engineers get themselves involved in? Okay, so if you are aware of a company known as SpaceX, okay, so this is an example of how the civilian space industry is growing at a rapid pace. It is being led by a few countries, United States, European countries, where a lot of commercial vendors, they are non-government linked entities, but they are contracted by various governments to build rockets and to build spacecraft that is capable of launching satellites and also bringing astronauts into space. Okay, so you might have read about reports around this industry. Okay, so it is a rapidly growing industry, and more startup companies are being formed to support this civilian space industry. What about aeronautical engineers? What are they going to be involved in going forward? At present, you know that there are drones So these are unmanned aerial vehicles. You don't have a pilot, and this is being operated by a pilot which is actually on the ground. So there's no pilot in the plane itself. So you have drones that are used for military purposes, but you also have drones that are used for civilian purposes like delivery. So this is an Amazon drone, is being used to for logistical purposes, is being used to transport items from one area to another. Okay, and closer to the Malaysia campus, we also have the Malaysian police putting drones to good use. And once again, this is pandemic related because we want to make sure that people are not crowding together. And what the police can do is they can keep tabs on people, but also broadcast public safety announcement just to make sure that people are abiding by all the safety guidelines. And if you are from Southeast Asia, you might be aware of this food delivery company known as Food Panda. So normally they send food to people who order them on the computer, on the mobile phone. And the delivery drivers normally come on a motorbike or scooter, or they may come in a car. But more recently, Food Panda is trialing the use of drones to deliver food, and they've been applying that to the offshore sector. So if you have got ship crew that's docked near to the coast, but they are some distance away in the sea. So how do you get the food across to them? So you can't have a driver in a car or a motorbike driving across to them. So what do? You make use of drones. Okay, so these drones are actually bringing food parcels over to the crew of the ship that's docked some distance from the shore. An example of what our students at Southampton get up to. Okay, so this is one project that our group design project students were involved in. So they designed a CubeSat, and this CubeSat is meant to monitor space debris. And what is space debris? If you keep sending satellites out into space, they operate for a number of years, eventually they go out of service. So they become space junk. So it's basically rubbish. And this image is a simulation of all of the space junk that is currently orbiting the Earth. If you keep sending up satellites and you don't keep track of them, you're going to have a problem, because these structures orbiting the Earth, they are going at speeds of the order of kilometers per second. So if you have an impact with your satellites that are still in operation, or if you have impact with your astronauts that are going around the Earth, it's going to cause major damage. That is why it is important for us to keep track of what we send to space. And that is the purpose of this mission. It is a microsatellite, and you can see that it is very small, fits on the palm of the hand. And these are our students giving their presentation at the European Space Agency. Okay, one small example of what our Aero and Astro students get up to. And in this particular case, they opted for the spacecraft design specialization. Okay, so now this is one image that I just want to show you before I end off my presentation. And this is an image which is actually related to the current situation with the pandemic. Major airlines are parked, they are not being used. And some people might be concerned, going forward, is there still going to be a need for aeronautical engineers? And the answer to that is definitely. So these planes are going to be put back into service once the pandemic is over. Okay, and they are not going to be parked there forever. And this civilian aerospace or civilian aviation industry is going to recover, is going to be important. And you're talking about, if you start your program, your degree program today, and you're going to graduate in 3 or 4 years' time, and by that time, that is exactly when the industry is going to need new engineers. Okay, so in summary, what is going to be important for mechanical engineers, for aeronautical engineers, for astronautical engineers, and any engineering specialization for that matter? Okay, so you will need to be equipped with awareness or even in-depth knowledge of artificial intelligence. You'll need to be taught how to apply data-driven solutions to solve engineering problems. Whether you're talking about cars or planes, autonomous systems will be coming into the forefront. You need to learn how to design these systems. And in order to design autonomous systems, you will apply advanced sensors because you need to be aware of what the environment parameters are before you can actually control your cars, your planes in the real world. Okay, so design is very important, not pen and paper design. You're going to be using software. That software is going to be equipped with artificial intelligence so that you can generate hundreds to thousands of designs within a single day. Okay, your traditional manufacturing processes are going to be important, but they will be upgraded. They'll be enabled, they'll be powered by computers, and they'll be controlled by these computers, and your manufacturing is going to be more efficient. It's going to be leaner. There's not going to be any wastage. You're not going to create lots of parts in order to store them in the storage somewhere, but you're going to have on-demand manufacturing and apply these to deliver these to your customers as and when they need them. All of these systems require lots of power. If you're going to store a lot of data in a data center, you need to power them. Okay, so fossil fuels, they will be phased out eventually. So that's why renewable energy is going to be very important. So think about the wind energy example that I talked about. It's one of many renewable energy sources, but mechanical engineers working in working and designing a wind turbine for a wind farm, that is a very plausible future career for a mechanical engineer. Okay, so I just want to show you these slides very quickly. I will not really dwell on them. University of Southampton, we are a top university in the world. Our engineering programs are ranked top 10 in the UK. So if you join us, it is a safe bet for having a good engineering training, and you will find that you are very employable once you graduate from the University of Southampton. Okay, and we're going to have a brand new campus, very exciting time for us. This year, September, we'll be moving into a brand new campus with well-equipped labs for engineering education. Okay, so I'll just stop here and I'll hand the time over to my colleague, Dr. Loh, who will be talking about the electrical and electronic engineering specialization. Okay, Ziha, back to you.
Yep, thank you, Dr. Swan. So we welcome Dr. Xiao Yong to continue.
Hi there, I hope that you can hear me fine. Ziha, is my screen looking okay now?
Yes, Doctor, you may proceed. Thank you.
All right, thank you very much. A very good afternoon, everyone. My name is Dr. Loh Xiao Yong. I'm the head of the EEE program here at USM. What I'll do today is that I'll just continue on with the discussion that Dr. Poo has given us, and then I will actually focus on electrical electronic engineering. What I'll do at first, in the first half of this webinar, is that I'll give a brief intro and insight into the world of EEE. And of course, in the second part, I'll concentrate on how you can actually achieve your aspiration to be an EEE engineer with us. Okay, now what I have here is actually a list of the main branches of engineering. Now, as you can see, I'm sure that these engineering branches are no stranger to you. We have civil engineering, chemical engineering, and mechanical engineering as introduced by Dr. Poo earlier on. And of course, we have the good old electrical electronic engineering. You know, these four engineering are really the main branches because we hear them so much. Of course, there are other engineering coming from sub-disciplines, but it's interesting to note that we can actually compare or draw comparison for these four major branches to a human body. Now, if you think about that, you look at civil engineering. What do they do mostly? The integrity of a structure, of a building. So that is akin to looking at the integrity structure of a human body, how we can actually stand up straight, how we are able to stand up supporting the heavy head we have, all right? Not design in a way that we have such a big head that, you know, we could lose balance as a result. Okay, so civil engineering, of course, all the piping in the internal system, all the waterworks. So that's all civil engineers. Okay, what about mechanical engineering then? I'm sure that you know more about mechanical engineering now after the talk. Well, I relate that to the joint system, the mechanical systems, and also we can also relate to the combustion system we have internally. That is, how do we actually convert the food into energy for us to move and walk in a way that we want it? So that's pretty much covered by mechanical engineering side. And then chemical engineering, all right, that has to do with the chemical processes in our human body, all right? So we have the chemical processes supporting the internal organs, and that's pretty much related to chemical engineering. Now, having said that, where does EEE sit then? All right, now, if you think about it, EEE has got to be here, all right? It sits right at the processor that we have, the good old brain, all right? So EEE will send, will receive the information data and then process them and then send out to all parts of the human bodies by using these electrical pulses so that we can control and function accordingly, all right? So it's actually quite an interesting comparison with engineering to a human body. And in fact, you can definitely see that quite a lot of inventions, ideas that we have actually draw inspiration from our own human capability, all right? Now, let me just let me just give you maybe one example on that. That's artificial intelligence, for instance, how we get inspiration to do that from our own capability. Now, Dr. Pu mentioned about sensors, right? Now, we have sensors. Our eyes can capture the image. Our ears can capture the audio. And our skin, we can feel the temperature, etc. So those sensors that we have receive lots of information. In fact, most of them are on most of the time, all right? We don't turn them off. Eyes, we can shut them off by closing eyes, but ears, they are on almost all over the time, unless, of course, you have been knocked out. All right, so, but the thing is, how do we process that huge amount of data? So this is where artificial intelligence comes about, which is very much how we manage that tons of information. The way that we process things, we do it without us knowing because it's just in us, all right? But if you try and mimic the same processes that we're actually using to process the information that we receive as a human being, then that's a very, very challenging area. And this actually gives rise to AI. So you can see that these artificial intelligence areas, we hear them so much, but you see it's never quite standalone. You need to get data. Where do you get the data? Sensors, different engineers doing that. And where do you keep those data? You must make sure that you have space for them, all right? So that's where the data storage people will come in, etc. And the processing. How do we process them? This is where artificial intelligence algorithms come in, all right? And what is it that we want out of this processing? We want to make it better. So we create algorithms to learn from the new data as they come in and fine tune and make it better such that it becomes like us, all right? We learn from experience. So that's kind of our data, all right? New experience come in, we adapt based on old experience. So this is a very, very nice example as to where the world of engineering is heading into, that is AI. But AI revolves really all aspects of engineering to make it a success. And this is what we talk about now. And And what they talk about is really Industrial Revolution 4.0, which is no longer the good old days like manufacturing and we're happy with it, but we want to make productivity level to be higher and more efficient, more intelligent, less human interference, put it that way. And we can do that through all the latest development and innovative ideas coming from engineering. Okay, now the next bit that I would like to share with you is about this triple E. Okay, now of course we can see from the previous example that triple E is contributing in its domain. All right, but the thing is, if you look more beyond that, why is it that we still have those branches of engineering in our degree program? That's because of the demand that we have. All right. If one day people don't demand for certain applications, then that area would definitely go down. Like, you know, for instance, there are lots of demands for the use of electronic engineers to support the various EEE applications that we use. Now, let me just give you another example. Say, for instance, in this COVID situation we have, what happens if we haven't got access to electricity? How is that going to impact our life? It's going to be horrible, if not worse, all right? Okay, now let's not go so far. Now just say if we lose Wi-Fi, we lose internet connection, what's going to happen? All right, that will be very bad. So this is where the demands comes from, and you need engineers to support all these demands, like the rise of electric cars, the rise of renewable energy, etc. Is because there's demands for it, okay? And we can definitely see that demand clearer by having a look at the jobs availability currently. All right, so I have actually done a quick survey early last year, but I did had a quick check this morning, and the trend pretty much follows the same. And what I've seen here is that from JobStreet Malaysia, I can definitely see that there are still quite a lot of demand for electrical electronics. And in fact, if you compare with other engineering areas, electrical electronic engineers are really sought after. And then if I go over to Singapore and just to double check on the data, I also get the same numbers. It's having a very, very high number of demands over in Singapore, just across the straits. And of course, number 2 on the list is actually mechanical engineering, which is very much needed as well. And of course, if I just draw a comparison to the UK website, Read UK, it's equivalent to JobStreet in Malaysia and Singapore, and the same demand applies. So we have done a bit of comparison for these demands over a number of years, and here I put up 2 years for you to actually have a look. And you can clearly see that of all the major engineering disciplines, EEE and mechanical are always up there, all right? And actually, we don't have to look so far. Like I mentioned, you just have to look around you. Look at the applications that you use just to maintain your life, just to make your life more comfortable, all right? And you need EEE engineers, you need mechanical engineers, and of course, you need other engineers as well to support you. But you can see the bulk of it actually comes from EEE and mechanical, okay? I will just go briefly about this. I won't actually drown you in factual information, but I would just like to point out something about the engineering programs that we have over at University of Southampton. Now, if you look at this university facts and figures sheet, you can see that 98% of Southampton graduates entered employment or further study within 6 months of leaving university. What that means is that 98% of graduates, upon graduating from Southampton, have either found employment or further their study, as in postgrads. 98%. And that is such a high percentage. All right. So that is why, you know, we are always proud of this motto that we have in EEE, that the graduates from EEE are actually not graduates. We call them engineers straight. So once they have graduated from the university, they are engineers, all right, well trained, sought after by industrial players, and that's why we managed to get this 90% high number there, all right. And of course, Triple E prides itself, and most recently, we have again been #1, ranked by Guardian University Guide in the UK. Okay, now I would like to share a bit with you on some of the things that we do at university and how that relates to real work. Now, as far as Triple E engineers concerned, there are really many facets of Triple E. What I've shown here are just some of the research areas that Triple E engineers actually do. Now, why do we do research before going into them? Is because, you see, this go hand in hand with the problems that we have in real life. So we have a lot of problems coming from trying to make our life better, and as a result, we actually need to find solutions for it. And in the midst of finding that solutions, we need engineers to work on it, either as a research engineer or different kinds of engineers to actually support the full development. And at Southampton, that's what we have, all right? Because all of our academics are at the forefront of research. We are actually working on solutions to today's toughest challenges, all right? And these are the 4 examples that I'd like to briefly talk to you about. Number 1 is really Southampton has invested so much in the area of nanotechnology that they have established this Zeppler Institute clean room, all right? And that's to the tune of £120 million so far, complete with state-of-the-art interdisciplinary clean room that would support nano, opto, electronics, quantum, you name it, all right? And one interesting facility that we have in this clean room environment is that we have this focused ion beam, all right, which specializes in nanostructuring of semiconducting dielectric metallic materials, all right? So what happens here is that you just want to restructure some of those small things at the nano level. And the team over at Southampton developed, in conjunction with Zeiss, the lens maker, a fantastic helium ion microscope to assist in the nanostructuring, that they can actually go down to sub-nanometer range, around 0.24 nanometer. That's the kind of resolution. And if you can't imagine how small this 0.24 nanometer is, you can relate to the size of this COVID-19 virus. On average, that's around 100 nanometer. And here, this kind of machine can go down to 0.24. So you can actually look how this COVID-19 is like inside out, all right? Because it's more than 400 times smaller than the size of the virus itself. And that's very small. And we can go as big as this high voltage stuff, all right? Now, what does high voltage relates to? That's high voltage engineering. So it looks at high voltage requirements, the transmission line systems, the conductive, induction, insulations, and all aspects, so that we can actually function as we need. As we grow, there's more and more demands for power, and hence the rise for all these related developments. All right, so you can see that Southampton itself, right, if you just look at the School of Electronics and Computer Science, it really covers all aspects of Triple E engineering, and you get the opportunity to actually just get to learn more about each one of these as you wish, all right? Okay, and of course, I'm going from the smallest to the biggest, and of course, we have all the in-betweens, such as this gate biometrics tunnel. So this is more related to AI. So now you are looking at the algorithm level, how you can actually make use of fantastic artificial intelligence algorithms, signal processing algorithms to actually get the right information out. And we have this printed electronics material. So that has to do with the sensors, like the human body. So this is looking at the sensors part. All right. How do we actually combine materials, the latest materials development with electronics to actually give us that that signals that we want, are able to detect certain things, and we're able to actually design the whole circuit boards on a flexi surface. So that actually gives rise to the development of what we see today, the fold handphones, the smartphones, etc. Okay. So I won't bore you with all this, but these are the broad range selection of projects that we have. The reason why I'm showing you this is because I want you to know that EEE encompasses a wide range of areas. It goes down to as small as nanophotonics level, as big as electrical power, and all the in between, all right? And of course, the trend now is really looking at the first two here, artificial intelligence, machine learning, cybersecurity, and systems, as we go more and more on this virtual setting, all right? And particularly on this artificial intelligence, because I think it actually draws a lot of interest from all parts, because it actually improves productivity and efficiency at a level which was very surprised by the researchers in the area as well. So I believe that there is still plenty of room to actually improve further on these aspects. And of course, this is where our students can actually get experience in and be at a head start, you know, when they actually finish their studies with us and continue to contribute to the benefit of mankind. And this is very much in line with the mission of our university to make the world a better place. All right. Now, I'm sure that you know with the EEE program, it's 2+2, and this is where you get to train up to be your pathway to be an EEE engineer. All right. So I'm sure that you know that in the first 2 years, you'll be doing that in Malaysia, and the last 2 years in the UK, where you get to look at or get involved in those group projects or individual projects that's relating to the research areas. Now, one thing I have to clarify here to a lot of students, a lot of prospects, that sometimes they get a bit fuzzy about this selection of projects. Now, in the first 2 years, you are doing all the fundamentals. All right, what happens is that you'll be looking at the design exercise life cycle of a EEE design system. And as you move on up in the years, the complexity increases, all right, in tandem as you progress, all right. But when it comes to third year and fourth year, you get to choose a wide selection of projects, which are sometimes referred to as the specializations. But they are really projects for you to get yourself into, to know more, because you're interested in that specific area. But that does not mean that if you're in a specific area, you can't move on to another area. The fact that you can choose from as small as nano to as high voltage as the high power labs, you can actually go into any areas of your choice. It's just that when you're doing those projects, you are focusing more on those part that you have actually selected. Okay. I would actually like to share something with you about these virtual labs that we have. Of course, with the COVID-19 situation that is hitting us, some of the classes will have to be made virtual. And of course, at EEE, we are very much lab driven. And to overcome some of the difficulties that we have, we actually send components and instruments over to our students so that they can actually continue on their journey with us to become the EEE engineer that they aspire to be. So this is one example that I would like to share with you. So what happens here is that there are certain labs in which that you need certain instruments for you to supply certain waveforms for you to measure certain things. And this is what we call bit scope, which is a multi-signal device, which can actually, here it is, which can actually function in an oscilloscope, function generator, logic analyzer. So that's the kind of setting that we have now to actually make the best out of the situation that we have, so that our students will not just be looking at the flat screen and looking at some demo, No, they are still experiencing the very nature of EEE as they go. And the good news about this is that once the labs finish, this instrument and components, they're still with the students, and we really encourage them to carry on, to investigate, to explore, get the curiosity going. And that's pretty much the essence of all engineers, all right? As the saying goes, curiosity kills the cat, but it was satisfaction which brought it back to life, all right? And that's what we really want to encourage in all the budding engineers that we have. Okay, now I would like to talk about the careers and employabilities with respect to the EEE engineering disciplines. Dr. Poo has shared on the many aspects that the engineers can get involved in. So I'll just summarize that quickly by showing the list of companies that our graduates have actually found employment with. All right. One interesting case is that, quite a number of our USM graduates, the ones that have actually transited to the UK, completed degree, and some of them actually continue to stay on in the UK as they found employment there. And they actually came back, and a couple of them came back, and they told me that they are now working with this JP Morgan. And you would actually think a bit, because JP Morgan, that's like a finance company, consulting firm, all right? EEE engineers in JP Morgan, all right? What do they do there? Now, they need a lot of software support. And especially with the rise of this cybersecurity, all the more they need that. And of course, artificial intelligence will come hand in hand. So that's why you see, as a EEE engineer, it is so versatile. You've got a good degree from a good university, and the program equip you with all the fine skills that you can readily use upon graduation, that you can proudly call yourself engineer at the point of finishing the program. All right, and the statistics speak for itself. So many of our graduates have found employment in various big companies and contributing, and they rise up to a good level and as part of their career development in those companies. Okay, this is where I'm going to end here, but of course I'm more than happy to accept any more questions if you have, if you'd like to know more about EEE. All right, thank you.